In this video, we will explore the implementation of stacks in the C programming language. We will cover two common methods: implementing stacks using arrays and linked lists. Stacks are a fundamental data structure, and understanding their implementation is crucial for writing efficient and organized code. Let's discuss the fundamental operations associated with stacks. First, we have push, which adds an element to the top of the stack. Next, we have pop, which removes the element from the top of the stack. Then peek or top, that lets you view the top element without actually removing it. isEmpty allows us to check if the stack contains no elements. Lastly, isFull is useful when implementing stacks using arrays, because it checks if the stack has reached its maximum capacity. Let's dive into implementing a stack using an array in C. To begin, we define a structure named stack. This structure holds three members. First, an integer pointer array, which will point to the base address of our stack. Next, we have an integer named top, which will hold the index of the topmost element in the stack. And finally, we have an integer named capacity, which represents the maximum number of elements our stack can hold. We can now use this stack structure to implement a stack. Then, to initialize a new stack, we define a function called createStack that takes capacity as its argument. Inside this function, we first dynamically allocate memory to the stack itself. We set the capacity field of the stack. We set the top to -1, indicating that the stack is currently empty. Then we dynamically allocate memory for the array that will store the stack elements based on the given capacity. Finally, we return the pointer to the newly created stack. Here's how we implement the push and pop operations for an array-based stack. For the push operation, the push function takes a stack pointer and an integer item as input. We first check if the stack is already full by comparing stack arrow top with stack arrow capacity -1. If it is, it means that we cannot add more elements, and therefore we simply return from the function. Otherwise, we increment stack arrow top, and then assign the new item to the array at that increment index. For the pop operation, the pop function takes a stack pointer as input. If the stack is empty, meaning that the top is -1, we return -1 to indicate that the stack is empty. Otherwise, we return the value located at the stack arrow array index stack arrow top, and then decrement the stack arrow top. This effectively removes the top element from the stack. Let's explore implementing a stack using a linked list in C. We define a structure called node, which will represent each element in the stack. Each node will contain an integer variable data to store the value and a pointer to the next node. Next, we define the stack structure. It simply contains a pointer named top that points to the topmost node in the linked list. Next, we define a function called createStack that allocates memory for a stack structure and sets its top pointer to null, indicating an empty stack. Additionally, a createNode function is defined to allocate memory for a new node, set its data field, and initialize its next pointer to null. Here's the implementation of push and pop operations for a linked list-based stack. In the push operation, we first dynamically allocate a new node and initialize its data field with the provided data. Then, we set the next pointer of the new node to point to the current top of the stack. Finally, we update the top of the stack to point to the newly created node, effectively adding it to the top of the stack. In the pop operation, we first check if the stack is empty by checking if stack arrow top is equal to null. If it is, we simply return -1, indicating that there are no elements to pop. Otherwise, we create a temporary pointer called temp, pointing to the current top of the stack. We extract the data from the top node. Then we update the stack arrow top pointer to point to the next node in the list, effectively removing the top node. Finally, we free the memory occupied by the temporary node and return the extracted data. Let's compare array-based stacks with linked list stacks. In terms of memory allocation, array-based stacks require a fixed size to be defined at creation time, whereas linked list stacks have a dynamic size and can grow and shrink as needed. Regarding memory usage, array-based stacks have efficient memory usage with no overhead for pointers, but linked list stacks require extra memory for storing next pointers. For overflow handling, array-based stacks can overflow if the capacity is reached, while linked list stacks have no overflow issues limited only by system memory. Implementation-wise, array-based stacks are simpler to implement. Linked list stacks require node structure and pointer management. In terms of performance, both achieve order of one-time complexity for push and pop operations. Lastly, regarding memory locality, array-based stacks offer better cache performance because of contiguous memory, but linked list stacks have poorer cache performance due to scattered nodes. Choose array-based stacks when you know the maximum size in advance and memory efficiency is important. Choose linked list stacks when you need dynamic sizing and don't know the maximum size beforehand. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.